Welcome to session 3 of our Catapult Academic training. Ray is going to be walking through some of the sample projects that we've got to show you what's possible and kind of some places to start, places that you can then build your projects off of. So without further ado, we'll turn it over to Ray, and if you have any questions, please don't hesitate to ask. Enjoy. Go for it, Ray.
Okay. So last 2 weeks, we have talked about Catapult hardware interfaces and the Catapult software APIs. So today, I would like to give some real examples. So in the V1.2 release, which is the current release, there are 3 sample projects, which is Pcie loopback stress test, DRAM loopback stress test, and the serialized 3 stress test. And we plan to release the serialized vector add, which targets multiple nodes in the next release. So today, I would like to introduce how these sample projects work. Before introducing the sample projects in detail, let me first give some basic ideas of how to build and run a Catapult project. So after you finished writing your source code, you need to do basically these 5 things to run it. First, you should use the quarters to synthesize the Fpga project. And quarters will generate a bit file in SOF format. And you should convert the SOF format to RPD format, which is accepted by our programming tool. Then you can program the Fpga with the RPD file with our programming tool. Then you are done with the hardware side. On the software side, you simply compile the host software program and run it. Here's one thing that you need to pay attention to before synthesize the project. There's a TCL file called project.tcl, which contains some shell parameters. So by default, the DDR feature and serialized 3 feature are all disabled. So if you want to use the DDR feature or serialized 3 feature, you need to explicitly override the parameter in the TCL file. You can also set the clock frequency here. If you think your code can run faster, like your timing constraints are all met with high positive slack, you can increase the user clock frequency here. Or if you think it's hard for you to meet the timing constraint, you can decrease the clock frequency. The seed value is for the synthesis tool to generate random numbers. Many CAD optimization algorithms take random numbers as inputs, and it will directly affect optimization results. If you are slightly off by timing or having some strange timing issues, it's sometimes useful to test different seed values, but do not use seed of 0. This is a known bad value and will almost guarantee a timing failure. We will not introduce how to use Altera quarters today. Please refer to Altera's website for quarters tutorials. They have very helpful tutorials, which I believe will help you understand how to use the tools. TimeQuest is a useful tool to analyze your project's timing. We recommend you to ensure that your project meets the timing constraints before running it, since running a bit string without meeting timing will result in unpredictable behavior and may cause you a lot of trouble. Signal tap is a useful tool to debug the FPGA. Sometimes your program does not run as you expected or even as you simulated. You can use signal tap to see what on earth happens on the FPGA, since it captures the real signal on hardware. It turns out that Manually converting the SOF file to RPD file is non-trivial. So we provide a script to help you easily convert the format. It's located in catapult release rows, and you can type this command with the path of input SOF file and the path of output RPD file, and to easily convert the files. To program the generated RPD file to FPGA, you should use the rsu.exe utility. You can type rsu-write RPD file to write the FPGA flash memory, or type rsu-reconfig to reconfig the application image. Do not use the Cortex programmer directly, or you will crash your machine. If you accidentally use it, you probably need to reinstall the driver and reboot the machine. rsu.exe needs administrator privilege, so you probably need to open a command window as an administrator and run the utility unit. There's another tool called FPGA diagnostic.exe. It is under Catapult release driver bin. Use this tool, you can directly read some share registers or soft registers by typing dash just read red. Similarly, you can write the register, use this tool. It's very convenient, and sometimes if you are running the serialize 3, you will config some register before your program, and you probably can use this tool to config it or to check it for running. Okay, so let's start introduce the project. The first sample project is PCIe Loopback project. It's a very simple Hello World example project. The host program basically send data to FPGA and expect the same data back from FPGA. As you can see from the figure, when host send data to FPGA, the simple row will get some PCIe packets from the shell, and it buffer it in the loopback queue, and then send the same data back through PCIe. The user logic is contained entirely in the simple row. You can slightly modify the PCIe loopback project by adding the soft register support. You can, instead of directly send the same data back to the host, you can increment all PCIe data by soft register value. You can see here from, in addition to PCIe packet, you can have soft register request, and you can store the soft register data in the register, and then add it to the PCIe packet data. Here are some project hints. First is don't forget the PCIe data is 128-bit, but words are 32-bit. So you need to add the data every 32-bit. You can either perform addition before enqueuing into loopback queue or after, but don't do both. You always update the registers every cycle, or else Cortex may produce a latch. Latch is a bad thing on FPGA. It is asynchronous and will potentially cause timing issue. Initialize register to 0 on reset. In software, write to the soft register using the FPGA write soft register API. You can do this. You can implement this design as a practice. Okay, the second sample project is DRAM loopback test. It is a more complicated variation of PCIe loopback test. Instead of directly send data back to host, it first writes it into the Pcie memory and read data back, and then send it back to the host. It shares the same host program as PCIe loopback test, but provides lower performance since it is bottlenecked by the DRAM read-write throughput. The project demonstrates how to interface with DRAM soft register and provide some useful library modules. We have talked about the simple DRAM module in the architecture section, which simplify the UMI interface. Here, the DRAM interleaver further simplify the simple DRAM interface in some sense. It has the capability of accessing memory in three modes: sending all requests to channel 0, sending all requests to channel 1, or interleave across both channels. The provided DRAM interleaver module actually sacrifices some performance. You can see it has only one input port. So to fully saturate both channels of memory, you need to design a dual-ported DRAM interleaver module, which is currently not provided. Loopback stress test host program is a host program for the PCIe loopback stress test and DRAM loopback stress test. To run it, you simply type loopback stress test.exe with the transfer size in megabyte, number of slots, and job size in kilobyte, and the mode. There are 4 legal modes. And the first mode is single-threaded in-order job completion. You can see in each iteration, we dispatch the work items to every slot. Then after iterating across every slot, we wait for the jobs to complete in the order in which they were dispatched. If the job is not ready, we defer the thread to prevent deadlock. And optimization to this will be performing useful work if the previous job are not yet ready, instead of wait. We observed that some jobs may take longer to complete than others. So we should look for jobs that are done rather than waiting for jobs to complete in order that they were dispatched. Rather than iterating over the for loop, now we use a while loop to check the jobs. If a job is not completed, we simply skip the job for now and check other jobs until all jobs are completed. One issue with the single-threaded technique is that we assume each slot computes job in lockstep, which means no slot can start a new job until all slots have completed a job. Also, job dispatch and waiting are sometimes on the critical path of the program. Although not shown in this example, it is common that data need pre-processing or the FPGA results need checking for correctness. So it is, in some sense, inefficient to send all jobs on the critical path. So we can use the parallel for construct in Microsoft Visual Studio's parallel patterns library to easily implement multi-threading to solve both of these problems. First, we replace the for loop with a parallel for loop with number of threads, num slots, which means we spawn one thread for each slot. Each thread will run a copy of the loop body in parallel, in which each thread sends a job, then wait for the job to complete before starting the next job. Of course, rather than simply waiting, And additional optimization would be to perform more useful work. One issue with the previous approach is that there is some delay between when a job completes and the next job begins, since it only has one job in flight per slot. So to fully maximize PCIe throughput, we can queue up many jobs per slot, such that the PCIe job dispatcher can immediately dispatch the next job after it completes a job. So rather than spawning one thread per slot, we spawn two threads, one for sending job and another for receiving jobs. Again, we use parallel for construct, but here we nest two loops such that each thread has a unique slot and ID pair. Here ID represents if a job is assigned to dispatch or is assigned to job completion. The X is the ID here. Okay, so here's a sample run of the PCIe loopback test. We can see the first one I run it in mode 0, which is single thread in order, and the throughput is 1.3 gigabyte per second. When I run it in mode 3, it can reach to about 2.2 gigabyte per second. Here's a sample run of the DRAM stream test, the DRAM loopback stress test. We transfer 4 gigabyte and we run it in multi-threaded with out-of-order job completion. And I also enable the DRAM interleaving. And we can see that the throughput is only 1.1 gigabyte per second. It is bottlenecked by the DRAM read and write in throughput. Okay, so the third sample project is Serialized 3 stress test. It provides a simple demonstration of how to use Serialized 3 links by sending data from one machine to another. As we can see from the figure, first, the sending node will send the PCIe data path. We send data to the Fpgas through PCIe. And when the simple row receives data from PCIe IP, it will buffer it in the loopback queue and send the data out through Serialized 3. The shell will handle the real data transfer in Serialized 3. And then the receiving node will receive the data, Serialized 3 data. And it will buffer it in the Serialized 3 receive queue, and then send it back to its host through PCIe. A single unified row is used for both the sending and the receiving FPGAs, and is configured through the soft register interface. As we talked before, there is no flow control provided for Serialized 3. So you need to implement your own flow control. Here in the sample project, we give a simple credit-based flow control. We use Serialized 3 out-of-band channel to return credits. Every time when the sending node sends a packet, it decrements the credit. The credit is initialized to 4K, which is the number of entries of the Serialized 3 receive queue buffer. But the out-of-band channel is a low throughput. So to prevent it from bottleneck the whole system, we return many credits at a time when the receiver has consumed the last packet of a message. So a message contains a lot of packets. It can, but if its size is larger than the size of receiving buffer, it will result in a deadlock. And the ideal maximum message size is half the size of the buffer to enable double buffering, which means when the sending node is filling half the receive queue, the receiving node can consuming the other half of the receive queue. And when the sending node finished sending the message, the receiving node will finish consuming the other half at the same time and return the credits, so that the sending node can start sending the next message immediately. The serialized 3 stress test host program is a simple program that measures serialized 3 bandwidth, and it is only compatible with the provided serialized 3 test role. The program demonstrates how to initialize and configure serialized 3 through the shell registers, determine serialized 3 status, and how to write a simple program targeting multiple machines with Catapult. So to run it, you can simply type serialized 3 stress test.exe with the transfer size in megabyte, number of slots, job size in packets. Note that here is in packets, direction and mode. The number of slots is between 1 and 64, with 8 near optimal in practice. Job size is in PCIe packets, and each packet is 16 bytes. Job size must be between 2 and 4096, which is 64 kilobytes inclusive. Direction is the serialized 3 port direction, which can be 0 north, 1 south, 2 east, or 3 west. And mode is either 0 send or 1 receive. Note that based on the current serialized 3 implementation, the host program on receiving node should be run first. So prior to sending data to FPGA, the host need to configure the serialized 3 registers first. The sample serialized 3 stress test role can only send data to one direction. We define a specific address of source register to be the direction to which the data is supposed to be sent. So set send port here basically do a soft register write to a custom defined address, and enable serialized 3 receive port does a shell register write. It enables the serialized 3 receive link. For the send node, you should specify the sending direction as well as enable the receive port to receive the out-of-band credits. For the receiving node, you just need to enable the receiving link. So here's the serialized 3 stress test sample run. And on the sending node, I send 4 gigabyte data to the receiving node. Here the node is receiving node is on the east of the sending node. You can see there is on number 2, ID 0 here. So it's on the east of the sending node. And on receiving node, it received the 4 gigabyte data. And the throughput is 1.1 gigabyte per second. Okay. And serialized 3 vector add is a simple example that can be run on more than 2 nodes. It basically adds up a lot of vectors. Here is an overview of the system. We run a head on one node and a follower on other nodes. The head will give a vector to its follower, and we store the vectors to be added to the initial node on the followers. Each follower will add one vector from the host to the vector from serialized 3. So the ring actually forms a pipeline. If you have multiple vectors that needed to be added, we can keep every node working, which means every host is feeding data to the pipeline. So the overall bandwidth will be the bandwidth of serialized 3 times number of nodes. So for a memory-bound application like vector add, we can potentially achieve very high performance. Here's the structure of it. In the sample project, we only use two nodes, and the follower directly sends results back to the head. Initially, both the head and the followers send the vector via PCIe, and the row will buffer it in the loopback queue. For the head node, it will send the data from loopback queue to the follower node via serialized 3. And when the follower receives data from SR3, it will buffer the data in the serialized 3 receive queue. And when both data are available in the serialized 3 receive queue and loopback queue, it will add up the data and send the data back to the head via serialized 3. Also, the head will, when the head receives the results, it will buffer it in the serialized 3 receive queue and send it to the host via PCIe. Okay, let me do a demo of the vector add project. So here's one of my machine. It's the 11B05. I use it as a head node, and you can see here. First, to run the project, first you open the project with quarters, and when you open it, you can compile the project by clicking the compile design. And it will take around 40 minutes to compile the design. And it will generate an SOF file located here, project.sof. And you need to use a script which is provided here. Generate rpd.ps1 to convert the SOF file to RPD file. I've converted the file here. And then you need to open a PowerShell, open a command window in administrator privilege. And you can write the image to FPGA using the rsu.exe, and then reconfigure it. I've already done it here. So after you write the FPGA, you can run the test with another command window. I forgot. You can compile the host program using Visual Studio. It is provided in the tech machine. You need to choose the release version with x64. And it will generate the output files, generate the compiled files in this directory. And you need to copy the INI file and the DLL file from driver bin. You need to copy the DLL files here. And then you can run it through the command window. Based on current implementation of serialized 3, you need to run it on the receiving node first, which means I have to run it on the follower node first. So The follower node is 11B06. So let me first run the host program here, and it will start waiting. First send the vector to the row and start waiting for the serialized 3 packets from the head. And then I can send data here. You can see that, yeah, here the head have received all the results in 3.4 seconds, and the throughput is almost the same as the serialized 3 stress test throughput. It's 1.2 gigabyte per second. Okay, that's all for the demo. So to summary, today I first introduced the steps to build and run the project, and I introduced the loopback stress test, DRAM loopback stress test, and serialized 3 stress test. I finally introduced vector add and do a demo on it. So, do you have any questions?
No questions? We did have one from David
asking
when the DRAM interleave module for dual ported memory access be provided.
We don't have a schedule now, but it's up to. But you can implement one by yourself. It's not that complicated.
Hey, thanks. This is David. I have a question. Thanks, Rob, for putting my initial question out. But the example on the vector addition with over SL3, if you don't mind, maybe going back to the slide. So I think what I recall is you're saying that the followers send the vectors to do the multiplication. I'm sorry, do the addition and then send the results to the head. What actually initiates the processing? Where does the processing start from? Is it from the head or from the follower?
So both the head and the follower's host will send a vector to the FPGA. And actually the head initializes the processing, and when the follower receives the data, receive the vector from the head via serialized 3, it will add it up and send the results back to the head.
Okay, because I was a little confused when you showed the demo where it seemed like you started off with starting one of the follower before then going back to the head to receive the results. So I didn't see where you sent the result, the actual inputs to the nodes.
Yeah, this is because based on the current implementation, we have to start the program on the receiving node first. So here, the follower will first receive vector from the head. So we have to start program on the follower first.
Oh, okay, I see. Yeah. Okay, I think I get it. So, is this sort of processing pipeline? So by that I mean, are you sending from the head to the first follower a vector, say for example, a vector of 10 elements? So you would stream in the first element to node 2, and then wait for the third element before summing them up, and it just pipelines that way to n, or you initially broadcast all of the vectors to all of the nodes, and then sort of subset what each node is actually computing on?
It's a pipeline. You can see it's a ring. If you want to, basically the system can add multiple vectors to add up multiple vectors. Here there are n vectors. you can add up n vectors. So here's a pipeline. When a vector goes through follower 1, it will add a vector on it. And when it goes through follower 2, it will add another vector on it, and then so on.
Okay.
Yeah, it's a pipeline. You can streaming on it, and if you have multiple vectors to be added up, you can keep it working.
I see. Yeah, I think it would have made a little bit. It would have been a little bit clearer if, say, there was maybe an initial slide that had a code of a very simple vector addition, or like just to kind of make it clear. As somebody said, it looks like fair filter. Okay. Thanks a lot. And another question that I had is, so you did the stress test, and the throughput was, I think it was on my note, 1.2 gigabytes per sec. What is the theoretical throughput for SL3?
The theoretical, I remember it's 1.5 gigabyte per second. It's the theoretical maximum. Yeah.
Okay, so it's pretty close, very close. Okay, that's very good. Thanks.
Any questions from anybody else?
I have another question. I'm sorry. So you gave so far, I think, 3 examples: a loopback, the DRAM access, and then the inter-FPGA communication through SL3. These are pretty good. They, I think, form some very good foundation for building any application. But I was wondering if there are already existing, like a full-blown application end-to-end that is already available in the Catapult repository attack.
No, in the academic program, I don't think there's a practical example. We just have these like test examples to start with. Yeah.
Okay, thank you.
Anybody else?
I have another question. Just looking at the slides. For SL3, how do you specify the address of neighboring FPGAs? So what I'm seeing from the slide right now is it looks like it's an ID going from 0 to, say, number of FPGAs. But I was wondering, for Catapult version 2, when that becomes available, this is probably not what it's going to be, right? Using IDs, it's probably going to be, excuse me, it's probably going to be, I don't know, based on some networking IP addressing scheme. Would that be correct? I think this question is also to Rob.
Actually, currently you use the direction to specify the neighboring FPGA.
Right.
Yeah, there's a so there's a network. The network, like which node is the neighbor of a node is provided, and you have to specify the direction when you want to send data to a specific node.
Right. Okay, so I get that part, thanks. But then in Catapult V2, there wouldn't be neighbors per se. There would be a switch, right? And those FPGAs will be connected to that switch. And I'm guessing there will be some way of addressing those FPGAs through an IP address. Correct?
Oh, I see. But yeah, this is not provided now.
Okay.
And I'm not sure, David.
Okay. Okay,
when
thank
we'll
you. Fingers crossed.
yeah. And actually, I
Yeah.
mean, that leads to a good kind of segue to, we're always looking for suggestions for future development and what might be useful in this environment. So if you've got something in mind, or you think of something that would be useful, by all means send it to us.
Okay.
And let us know, and we can then assess that and determine whether or not it's a direction we want to go with the academic shell. So we are constantly looking for feedback from our researchers. So and so this goes to everyone out there listening today. Have a question, or you have something like that you think would be useful for future development, by all means let us know. I can say I've had a lot of people join the listserv over the last few weeks, so we might be working towards a point. I would like to develop some sort of platform forum so that we can kind of get folks talking with each other. I know that we do have the listserv, but it's not particularly interactive. So I'm looking at some options to provide some sort of platform for some better communication and sharing amongst our researchers. I think that would be useful.
So, David here. So, Zoltan and I have actually been talking over email, and thanks, Rob, for making that introduction.
Absolutely, and I'm happy to do that for anyone.
Yep.
So I will. I've sent a couple of messages out, on Zoltan's behalf, what he's working on and looking at. But if again, if we have some sort of platform that we can communicate a little bit better on, we're going to try to use that. But right now, I just don't know what that's going to be.
So there's actually a tool that is very good for collaboration and kind of keeping track of projects. It's called Asana. I don't know if you've used it before, but I use it a lot and it's quite effective.
Asana?
Yes.
I'll take a look at that.
Okay.
Appreciate that, David. Okay. Any other questions? All right then.
One quick one. When is OpenCL going to be ready? I know.
We're hoping imminently, especially since we got to try to do a class on it next week.
Right.
So we're dealing with some hurdles there, but we're hoping soon. I can't give you anything more firm than that, Dave. Sorry.
Okay. All right. Thank you.
Yep. Anybody else? Any other questions? Okay. Thank you, everybody, for your time. Enjoy your weekend, and be on the lookout for notices on posting the video and the slides. And if you do have anything, any questions, please don't hesitate to send us out a message. So have a good weekend, everybody, and we'll hopefully see you next Friday.
Thank you. Have a good weekend.
Thank you.
Thank you.
Bye. Bye, Ray. Bye, Rob.
Bye-bye.
Bye.